So the question is, with the help of state diagram or state graph, state and transition table and timing diagram, explain sequential parity checker. So what is the use of this parity checker? Parity checker is mainly used for your error detection. Okay. So we can define that when a binary data is transmitted or stored, an extra bit that is called as a parity bit is frequently added for the purpose of error detection. Okay. If the data transmitted is group of 7 bits, then 8th bit is added. 8th bit will be the parity bit is added for error detection. So this is your example. So in this example, you can see that these are your 7 bits, 00000. It goes on. Okay. And you have an 8th bit. This will be your 8th bit. That is nothing your parity bits. So the total of these 8 bits will be your 8-bit word. This is an example for your odd parity. This parity can be divided into two types. One is called as odd parity and the other one is called as even parity. What is meant by odd parity? If the total number of ones is odd, then it is called as odd parity. For example, see here, in the 7 bits, you don't have any ones, right? So it is 0. It is an even. So if you want to make it as a, this example is for odd parity. If you want to make it as odd, then you have to add an 1 in your parity bits. Similarly, in the second case, you can see 000, you have only 1. So it is odd. Already it is odd. So you are going to make a parity 0. So in the third case, 1, 2, 3, 4, you have 4 ones. So it is even. So you have to make it odd. So you just make the parity bits accordingly and you transmit. In the receiver side, if there is any difference in this data, you can know that the error has been occurred or the error can be detected. This is how the procedure follows. Okay. Now, the second type is your even parity. If the total number of ones is even, then it is even parity. So next, let's see the block diagram of your parity checker. Okay, the block diagram consists of the parity checker. The input is going to be your X. What will be the input sequence of zeros and ones? And your output is going to be your Z. Z will be equal to 1 if it is odd parity and Z will be equal to 0 if it is an even parity. Right. So odd parity means if odd number of ones is there, and even parity means if even number of ones is present. So always your X will be loaded depending on your clock signal. Okay. The values of X will be read at the time of the active clock signal. There is no bubble. So it is active clock edge. So what is the use of this? One more use of this clock input is in order to distinguish the consecutive zeros and ones in the X input. Okay. This is one of the advantage of using the clock. Okay, so in the previous example you have seen that it was for odd parity, right? So if an even parity has occurred means you know that the error has been occurred. Okay, if any one parity, if this is equal to 0 means even parity has occurred means you know that the error has been occurred. So the second one is your state diagram, right? State graph or your state diagram. So you know that the sequential circuit must remember whether the total number of ones is odd or even. So how many states you will be having? Obviously you will be having 2 states. Let us take the 2 stages. So let me take the next diagram, state diagram or state graph. Okay. So let me take the 2 states. One is S0 and the other one is S1. The 2 states. So what will be your S0? S0 is for even number of ones and S1 will be for your odd number of ones. Okay. So depending on this you can draw your state diagram. So let me take the 2 states S0 and let me take the next state as S1. Okay. So S0, what will be the value for your output? Z is equal to 0. For S1, Z will be equal to 1. So this will be your output. Now, for the first case, if X is equal to 0, means what? The 0 means initially, let me assume that the data is equal to 0. All zeros are being transmitted. So, when I give the input X is equal to 0, there is no ones, right? 0 is an even number. So, it will be remaining in the same state itself. So, this will be your graph. Okay. Now, if X is equal to 1, now what will happen if X is equal to 1? Now, you have one occurred. So X is equal to 1 means it will go to your odd state, right? number of 1 will be equal to 1. So what will happen from the S0, S0, it goes to the second state S1. Okay, there will be a transition. Similarly, for the second state, let me consider. So case 2, if S1 is equal to, S1 is the state. Now I am giving input is equal to x is equal to 0. If x is equal to 0, still your 1 will be in the odd value, right? S1 will be, output is equal to 1 because it is an odd value. So it will remain in the same state itself. Now if x is equal to 1, what happens? 1 plus 1, it will be 2. It will be even. So it will go to the next state. So if x is equal to 1, there will be a transition. So this will be your state diagram. So what are the two cases for your, so let me write here. So you have two cases, right? Case 1. What will be your case 1? So in case 1, initially your, what is the initial case? Initial case, you are receiving all the input to be, the state is, initially it is in the state S0 because you have all the inputs, initially zeros have been received. Okay. And 0 is an even number. Now if the circuit is equal to, now let me take the two condition. The circuit is in the state S0, then you are getting, you are sending an input, x is equal to 0 is received. Then what will be happening during the clock? Then what will be happening when x is equal to 0? There will be no change. It remains in the state. Okay. Now if x is equal to 1, what happens? It changes the state from S0 to S1. Similarly in the case 2, now you assume that now you have your state is changed to S0 to S1. So during the S1, if when you are applying the input x is equal to 0, what will happen? There will be no change. Right. Now when x is equal to 1, 1 plus 1, it will be 2. So it will be changing from S1, changes the state from S1 to S0. So this is your working principle of your state diagram or your state graph. So your next question is to draw your state table and your transition table, right? So in order to draw your state table, let me take the next paper. So state table. So state table, and the next one will be your transition table. So what will be your state table? State table gives the values of your present state and the next state, right? So if I can make a table, so this will be your present state. What will be your next state? Depending on the inputs. Next state. So this is going to be your state table. Okay. So what will be your present state? You have two states. One is S0 and one is S1. Okay. So your what will be your next state? Next state will be depending on your inputs x is equal to 0 and x is equal to 1. So if it is in the present state S0, now what will be your, if your input x is equal to 0, it will remain in that state. There is no change. If x is equal to 1, it goes to your next state, that is S1. Similarly, when it is in the state S1, if x is equal to 0, there is no change. It remains in S1. If x is equal to 1, it goes to the previous state, that is your S0. So you have one more column. So what will be your present output? So what will be your present output? Depending on your present input, present state. If it is S0, your output will be equal to 0. If it is S1, your output will be equal to 1. Okay. So this will be your state table. Now what about your transition table? Transition table will be giving you, let me take another color. It will give you, which gives the next state of the flip-flop as a function of their present state and the circuit inputs. So what will be your table components you have? So one will be your present state. Depending on your present state, so this will be your next state q plus, depending on your x is equal to 0 inputs, x is equal to 0, x is equal to 1. The same two steps in the previous state table you are going to write here. And what are you going to add? The input to the flip-flop. The flip-flop which you are going to use here is T flip-flop. So depending on the inputs, what is your flip-flop states? That is the transition table. So what will be your states here? Present state is 0, 1. what will be your x is equal to 0 means there is no change. So it will be in 0 itself. If x is equal to 1, the state will be changed. Similarly, what will be if x is equal to 0, there is no change. It will be in that state. When x is equal to 1, there will be change. So it will go back to 0. Now what will be the input? So now for the T flip-flop, what you have to do here is, if there is a transition between your present state and your next state, the value will be, input will be equal to, input of the flip-flop will be equal to 1. If there is no change, then it will remain 0. See, in this case, q is equal to 0, x is equal to 0 means your q plus is equal to 0. So what will be happening here? There is no change, so it remains in 0 itself. But whereas in this case you see q is equal to 0, q plus is equal to 1, there is change. So your value will be equal to, input flip-flop will be equal to 1. Now what is happening in this case? Q is equal to 1, x is equal to 0, there is no change. So your value will be equal to 0. Q is equal to 1, q plus is equal to 0, there is change. So your value will be equal to 1. So what will be your output? If you take one more column as your output, what will be your output? Z will be equal to, depending on your present state, what will be your Z? 0, and it will be 1. Okay. The overall output will be, if it is q is equal to 0, your output will be equal to 0. If q is equal to 1, your output will be equal to 1. So this will be your transition table. So depending on this, can we draw the T flip-flop? Okay. So what will be your T flip-flop circuit diagram? You will be having your clock. So this is the clock activated for your negative trigger, negative edge triggered clock. Input is T, x will go to your T, and there will be two outputs. One is your Q and other one is your Q dash. Q will be your output Z. So this is your parity checker using T flip-flop. Okay. Now what will be your last question is your timing diagram, right? So timing diagram. So how will you draw your timing diagram? So suppose if I take the data x is taken 1 0 0 1 1 0 1 0. So if this is your data, okay, so here it is 1 0 0 1 1 0 1 0. Now depending on your clock, so here you will be having your clock signal. So if this is your clock signal, what will be your output? So what is going to be your output? So the clock here is negative triggered, right? So negative edge. So whenever there is transition in 1, x is equal to 1, you will be having a change in the state. So here you have 1, right? So during the negative edge. Similarly here you have 1. So during these transitions you will be having, during this clock you will be having your transition. Here you have x is equal to 1. So during the negative edge you will be having transition. So initially your flip-flop output. So if this is your output Z will be equal to your Q. So initially your output was equal to 0. So here you have input is 1. When input is 1, you will have a transition during the negative clock. So here it will go to 1. Now it is 0. So it remains in that state. Here you have x is equal to 1. So here you have clock negative. So here you will be having a transition. Similarly here again your x is equal to 1. The transition happens in the negative edge of the clock. So again here you have a state change. It is in 0. It remains in that same state. Now x is equal to 1. Again during the negative trigger, negative edge, what you will be having? You will be having your transition. So this is how you will be getting your output. So totally your last state is in the 0. Why? Because it is an even parity, even number of ones, 1 2 3 4. Right, so you will be getting it, you will be remaining it in Z will be equal to 0 because it is in even parity. So this is your explanation of your parity checker with your state graph, state table, parity checker, and your flip-flop diagram.